continue where we ended in the last lecture, which was lecture 34. In this lecture 35, we will be solving the problem that we had discussed in the last lecture. So, just to give a recap, we have a skin stringer idealized C-section. There are 4 booms of equal area 300 millimeter square at the 4 corners, which are 1, 2, 3 and 4. A shear force Sy, which is 4.8 kilonewton, is applied in the y direction at a distance through the shear center. So, we have to find out the shear flow in the cross section and the shear center of the cross section. As we know that the cross section is symmetric about x axis, the shear center is going to lie on the x axis, and let us say that the distance of the shear center is zeta from the vertical web, that is 2, 3 of the cross section. Now, since the cross section is symmetric, Ixy is equal to 0, and since the shear force is applied only in y direction, Sx is equal to 0. By implementing or enforcing these conditions in the equation for shear flow, we can simplify it in this form. So, this is the simplified form of the shear flow equation for a symmetric beam where only Sy is being applied. So, let us now try to solve this problem. So, let me write this down as Qr plus 1 minus Qr is going to be minus Sy by Ixx into Br into Yr. So, this is the expression that we have. Now, the first thing that we have to do is to find out Ixx. Now, if we have Ixx, let me just quickly in a rough sense draw the cross section. So, this is 400 and this is 200. This is 1, 2, 3 and 4. Now, this is the rough sketch of the cross section. Now let us try to find out Ixx. Now, Ixx is going to be there are 4 booms, each of area 300 millimeter square, and each of this boom is located at a distance 200 millimeter from the x axis. So, therefore, it all has 200 distance. So, the total Ixx is this one into and the unit would be millimeter 4. So, if we find this, this is going to be 48 into 10 to the power 6 millimeter 4. Therefore, in this expression Qr plus 1 minus Qr, this can be written as minus 4.8 into 10 to the power 3 by 48 into 10 to the power 6. Br is always 300. So, 300 into Yr. So, this is the expression that we have. Now, let us try to find out the shear flow. So, now for flange 1, 2, we have Q12 minus Q0, which is going to be equal to 0 because this is the open end, and that is going to be minus 4.8 into 10 to the power 3 by now Yr is going to be that of Y1. and this is B1. So, if I simplify this, I am going to have minus 4.8 into 10 to the power 3 into 300 into y1 is therefore going to be plus 200. So, this turns out to be minus 6 Newton per millimeter. So, because this and this becomes 48, so I have minus 6 Newton per millimeter of shear flow. So, therefore, Q12 I can say is minus 6 Newton per millimeter, and our S coordinate is taken in this direction. So, this is I have taken to be the positive direction of S. So, Q12 is therefore minus 6. Now, let us go to for web 24. Now, for web 24, Q23 minus Q12 is going to be minus 4.8 into 10 to the power 3 by 48 into 10 to the power 6 into B2 into Y2. Now, in place of B2 and Y2, I can write minus 4.8 . Now, B2 is going to be again 300 because all the booms have the same area, and Y2 is again positive 200. Therefore, Q23 is going to be minus 6 Newton per millimeter plus Q12. Now, Q12 is again minus 6 Newton per millimeter. So, therefore, this is going to be minus 12 Newton per millimeter. So, therefore, I have Q23 is equal to minus 12 Newton per millimeter. So, this is the solution for. Now, let us find out for flange 3-4. Now, I will have Q34 minus Q23 is going to be minus into Q, it is going to be B3 and Y3. So, in place of B3 and Y3, I can write B3 is again 300 and Y3 is minus 200 since it is in the minus direction. So, therefore, Q34 is going to be 6 Newton millimeter plus Q23. Now, Q23 is minus 12 Newton per millimeter. Therefore, Q34 is minus 6 Newton per millimeter. Therefore, I can write that Q34 is going to be minus 6 Newton per millimeter. So, now I have obtained the shear flow. Now, let me draw the cross section once more. I have a shear force which is let me name them as 1. Now the shear flow that we have calculated is minus S, from right to left was considered to be positive. Now since this is minus, this is the direction of the shear flow that I am going to have. So this is going to be 6 Newton per millimeter. This is going to be 12 Newton per millimeter, and this is going to be 6 Newton per millimeter. So this is the shear flow that we are going to have, and as you can see that the shear flow is constant in any portion between two booms. Now let us see a big advantage of using skin stranger idealization. In a regular thin wall beam, to obtain the shear flow, we have to perform a integration, as you have seen in the previous lecture. Finding out or evaluating those integral was a tedious task, making the solution of shear force problem a cumbersome problem. Now you can see in a skin stranger idealized cross section, finding out the shear flow is much less tedious or much easier as compared to normal thin wall beam, and therefore can give us very quick solution or estimate of the shear flow in a cross section. Now my next job is to find out the shear center. So let us try to find out the shear center. Now let me again draw the cross section. So I have a shear flow of 6 Newton millimeter, 12 Newton millimeter, and 6 Newton millimeter. And then I have a shear force Sy equals to 4.8 kilonewton, which is at a distance zeta from the vertical wave. So let me put the name 1, 2, 3 and 4. Now to obtain the shear center, the point about which we should take the moment should be carefully chosen so as to minimize the calculation required. I will reiterate that we can choose any point and find out the moment, but then the calculation might become tedious. So we have to wisely choose a point to take the moment so that our calculation remains as simple as possible. So for this problem we will choose the point 2, because if we choose point 2, the only shear flow that is going to produce a non-zero moment about 2 is that of Q34. Therefore, our calculation would be much more easier. So therefore, by taking moment about point 2, point 2, what do we get? We get Sy into zeta is going to be 6 into 200 is the length, okay, into the moment arm, which is going to be 400. So this is how we can actually find out the shear flow. So Sy is basically 4.8 into 10 to the power 3. Therefore, we have 4.8 into 10 to the power 3 zeta, and that is going to be equal to 48 into 10 to the power 4. So that gives us that zeta is equal to 100 millimeter. So, this is the answer that we have. So, this shear center is 100 mm from the vertical web to 3. So, now we can see that finding out the shear center for a actual cross section would again be immensely cumbersome. We have to do huge calculation to find out the shear center for a actual cross section. But when we do skin stringer idealization, the problem is simplified to a great extent and therefore can give us quick solutions. Next, let us solve. So, we have solved an example on an open cross section beam. Let us solve the example of a closed cross section and see how we can find out the shear flow there. As discussed, so let us consider this example, which is a closed cross section, and there are booms at each corner. All the dimensions are given in millimeter. The red color number shows the area of the respective boom in millimeter square. So, when we solve the problem of shear flow in a closed cross section beam due to shear forces, in the week 6 we had seen that the only difference between finding out the shear flow in a closed cross section beam and an open cross section beam is that we have to assume the shear flow at a certain point, and based on this assumed shear flow we need to find out the entire shear flow. And then if the shear force passes through the shear center, we have to use the Bret-Bethes theorem and find out the assumed value Q0. So, the same process has to be applied in a skin stringer idealized cross section as well. There would be no difference in the process of finding out the shear flow in a closed cross section beam. The only thing that would be different is that because the shear flows are going to be constant in each of this portion, the calculations will become extremely straightforward. So, let me write down the problem statement. The problem statement says that find the shear flow in the cross section due to Sy equal to 10 kilonewton applied through the shear center along the, so Sy is in the y direction. So, I can say that somewhere here we are applying an Sy which is 10 kilonewton and it is acting through the shear center of the cross section. Now, let us do that, let us assume. So, since this is symmetric about x axis, so this cross section is symmetric about x axis. So, let this be the x axis and somewhere here is the y axis. So, this is the centroid. So, this is symmetric about the x axis. So, I x y is going to be equal to 0, and since only Sy is being applied, Sx is also equal to 0. So, if we implement this conditions into the equation to find out the shear flow, we can simplify this as Q r plus 1 minus Q r is going to be minus Sy by I x x into BR into YR. So, Ixx of this cross section can be found out very easily, and I am not repeating the calculation here. If we find it out, it is going to be 13.86 into 10 to the power 6 millimeter 4. So, therefore, let us assume that the shear flow in 2-3 portion is Q0 and it is in this direction. So, this is the direction of S. So, we are going to assume shear flow in 2-3, that is Q23 is going to be Q0. So, this assumptions need to be made. Now, once as we have done previously for a conventional thin wall structure. So, now let us try to find out the shear flow in the other cross section. Now, Q34 minus Q23 therefore is going to be minus 10 into 10 to the power 3 by Ixx, which is 13.86. Now, BR is going to be B3 into Y3, which is going to be minus 10 Now, BR is 400 and YR is going to be 100. So and therefore, which is going to be equal to 28.9 Newton millimeter minus of that, and that is equal to Q34 minus Q23, which implies that Q34 is going Q23 we are assumed to be Q0. So, Q34 is therefore 28.9 plus Q0. So, that is how we have got Q34. Now, let us try to, so let me just write it down here. So, Q34 is minus 28.9 plus Q0. So, then let us similarly find out the other shear flows. So, if we find out Q45 minus Q34 is going to be minus 10 into B4. B4 is 100. So, this is B4 and Y4. Y4 and Y4 is going to be 50. So, this is Y4. Now, if I calculate this, this is going to be minus, so then we have Q45 is going to be minus 10 into 100 into 50 plus Q34. Now, Q34 is minus 28.9 plus Q0. Now, if we evaluate this, this is going to be minus 32.5 plus Q0. So, this is Q45. So, this is Q45. So, similarly, we can find out the shear flow in each of the portion of the cross section. So, let me skip these steps and try to find out the shear flow in each of the cross section and write it down in this figure. So, this is 2, this is 3, this is 8. Now, if I draw the shear flows in each of the cross section after calculating this, this is going to be Q0, this is going to be minus 28.9 plus Q0, this is going to be minus 32.5 plus Q0, this is going to be minus 28.9 plus Q0, this is going to be Q0, this is going to be 18.1 plus Q0, this is going to be 22.4 plus Q0, and this is going to be 18.1 plus Q0. Now, since the shear force is passing through the shear center, we can use Bred-Bethos theorem and say that tau ds has to be equal to 0, just because it is passing through the shear center. Now, since the cross section has an uniform thickness, this can also be written as Q ds is equal to 0. Now, if we have to find out this Q0, so then we have to find out the Q0 and take the summation over the entire cross section. So, this is going to give us Q0 100 for the 2 plus 60 for the 2 vertical web plus 2 into 240 for the 2 horizontal wave, and then we have 2 into 120 square plus 50 square plus 2 into 240 square plus 70 square into, that is going to be equal to minus 28.9 into 2 into 50 square plus 120 square. Then we have minus 32.5 into 100 plus we have 2 into 18.1 into 240 square plus 70 square, and then we have 22.4 into the vertical web 60. Now, if we calculate this, then Q0 is going to be 0.264 and that is equal to 0. Therefore, we can say that Q0 is going to be 0.264 Newton per millimeter. Now, this once we find out Q0, we can find out the shear flow in each component of the cross section. So, this is how we can see that we can easily find out the shear flow in a closed skin stringer idealized cross section. The calculation is much more simpler when we make such idealization. Thank you.